So what I want to do in this video is I want to analyze the different types of motion that an object can have. And so what I have over here is a circular object, and I want to analyze the motion of rolling without slipping. So here's the circular object that can roll, and let's say that on the surface of the circular object, let's say I coat or I paint the surface of the object with green paint. And then let's say I push the ball forward. If I were to push the ball forward, then what would happen is that this green paint that's on the surface of the ball that I just painted on would get traced out onto the surface, and it would look something like this. Because all of the paint that's that's on the surface of the ball will get traced out onto the floor, meaning all of the paint that's on the ball or on the surface of the ball, all of that is going to trace out onto the floor as it rolls. And so the object is going to rotate as it moves forward. And so the length of this green paint right here that's on the floor, the length of this green paint is just going to equal the length of this green paint that's on the surface of the ball. Since we just push the ball forward, all of the paint that's on the surface of the ball is just going to get uh, traced out onto the floor. So these two green marks, so these two green lengths right here, this length and the length that's on the ball, these two lengths are actually equal to one another. Meaning, so what we can get from this is that as the ball moves forward a distance that's equal to this arc length right here, since these two distances are equal, or these two lengths are equal. So how much ever length of paint that's on the surface right here, that's equal to the length of the paint that's on the surface of the ball, which is the arc length of the ball. And so what we can say is that the length of the paint on the floor or on the horizontal floor, that's equal to the length of the paint on the ball. And so we can write an equation. So if we consider this distance right here, this distance that I just drew out, that's equal to the arc length that's of the paint that's painted on the ball. And so we can write a formula for this to calculate this horizontal distance that's traced out by the paint on the floor. So let's say that, so we know that this distance that's on the floor, that has to equal the arc length of the paint that's on the surface of the ball. And the formula we have for arc length is, let's denote the arc length with an S, and that's equal to the radius of the ball times the angular displacement. And the angular displacement, that's just the angle in which the ball rotates through. So let's say the initial angle that the ball starts at is theta subscript I for theta initial, and the final angle that the ball ends up at is theta final, or theta subscript F. So the change in angle, or the change in the angle, is given by the difference between these two angle values, or the change in theta. So this is the arc length that the paint covers, and it's on the surface of the ball. And that arc length is equal to this path that gets traced out onto the floor by the green paint when we give the ball a push forward, or when the ball rolls forward. And so this equation right here is the arc length formula. And so the arc length of the paint on the ball is equal to the distance that gets traced out onto the floor. And so let's look at the center of mass of the ball, which is at this green dot right here. And so when we push the ball forward, the center of mass, it also moves forward. It moves this distance forward. And so the center of mass, it travels a distance that is equal to the length of the green paint that's on the floor. Because notice how these two lengths are equal. The length of the green paint that's on the floor is equal to the length of the path that's traced out, or that's traveled by the center of mass. So the center of mass travels a distance that's equal to the arc length, and the arc length is equal to the distance, to this distance that's traced out on this floor. So we can write that the distance that the center of mass travels is equal to the arc length of the paint that's on the surface of the ball, and that's equal to r times the radius times the angular displacement. And so let's divide both sides of this equation by the change in time. Meaning, let's divide both sides of the equation by the amount of time that it took the ball to roll this entire distance right here that's traced out by the green paint. And so we'll call that change in time a change in t, for change in time. If we divide the distance that the center of mass travels by a change in time, then we know that a distance divided by a change in time is just equal to a velocity. So the distance that the center of mass travels divided by the time that it took to travel that distance is just equal to the velocity of the center of mass. And that's equal to the radius times the change in angular displacement over time, which would give us the angular velocity, which is denoted with a omega for angular velocity. And since the ball is rolling forward, it's going to rotate, and so it's going to have an angular velocity, which is denoted with this omega. And so this condition that we have right here, that the velocity of the center of mass is equal to the radius times the angular velocity, this condition is known as the non-slip condition. Meaning, if we want an object to roll without slipping, this is the condition that has to be satisfied. So if we want a object to roll without slipping, that means that the velocity of the center of mass has to equal the radius of the object times its angular velocity. And so let's say that this equation was not satisfied. Or let's say that if there was a scenario, let's say that if the velocity of the center of mass did not equal the radius times the object's angular velocity. That means that the object would not roll without slipping. Or meaning, that means that the non-slip condition would not be satisfied, and then the object would not be able to roll without slipping. Meaning that this condition is not satisfied, and so that the object will roll with slipping instead of rolling without slipping. So for an object that rolls without slipping, the condition that the velocity of the center mass has to equal the radius of the object times the angular velocity in order for an object to roll without slipping. So this condition has to be satisfied in order for an object to roll without slipping. If it's not satisfied, then the object will instead roll with slipping, or it will just translate forward. So now we're going to analyze a couple of different scenarios in which an object it undergoes rolling with slipping and rolling without slipping and just pure translation. So here I have three different scenarios in which a circular object undergoes three different cases of rotation. So initially the object is on a frictionless surface and it travels at an initial velocity of v naught. And then the surface has no friction, and then it encounters a surface with friction, and the coefficient of friction has a coefficient of mu. Now when it encounters the rough surface, it's going to slide and rotate, and then eventually it's going to reach a final velocity and it's going to rotate without sliding. So we're going to analyze each of these three different scenarios in detail. But first, let's consider the first case in which the object simply slides only. So if the object is sliding only, what that means is that since there's no friction present, that means that there can be no force to produce a torque about the object's axis of rotation, and so the object will not be able to rotate. Instead, the entire object will just translate forward with an initial velocity of v naught because the surface is frictionless. And so there can be no force to produce a torque to cause the object to rotate. And so the entire object just travels forward at an initial velocity of v naught. And so the object will not be able to rotate. So because the object is sliding only, that means that each of the points, each individual point or any point on the object will also travel at this initial velocity. So what we can say is that the center of mass of the object, which is at the center of the object, the center of mass's velocity is equal to the initial velocity because the object is sliding only and the surface is frictionless. So every point on the object's surface travels at the same initial velocity. So the point on the bottom of the object also travels at the same initial velocity, and the point at the top also travels at the same initial velocity, and so do any other points on the object. any other point on the object also travels at the same initial velocity because the object is sliding only. Another way to say sliding only is just translating only. And so we know that since the object is sliding only, it only has a linear velocity, but it doesn't have a angular velocity. So the angular velocity is 0, but it does have a translational velocity. And the angular velocity is 0 because there is no friction to cause a torque to cause the object to rotate. So that's why the angular velocity is 0. So now we want to check if the non-slip condition is satisfied or not. And remember back earlier where we derived the non-slip condition, we just said that the velocity of the center of mass has to equal the radius of the object times its angular speed, or its angular velocity. So would the non-slip condition be satisfied in this case, or would the non-slip condition not be satisfied in this case? So the velocity of the center of mass is just equal to the initial velocity. But remember that we said that the angular velocity is 0. So the initial velocity is equal to the velocity of the center of mass, but the angular velocity is equal to 0 since it has no rotation. So what we can say is that the velocity of the center of mass is actually not equal to the radius times the angular velocity, but instead, since the angular velocity is 0, if we plug in a 0 for the angular velocity, this entire term goes to 0. And so what we can say is that what we can write is that the velocity of the center of mass is actually greater than the radius times the angular speed because the angular speed is 0. So if we multiply the angular speed of 0 by the radius, this entire term just goes to 0. And so the velocity of the center of mass is going to be greater than 0. So the non-slip condition in this case is actually not satisfied. Now let's describe the motion of the circular object. So remember that since the object is sliding only, that means that any point on the object is also going to have the same initial velocity. And so that means that we also said that the angular velocity is 0. And so we can just treat this circular object as a normal mass or a normal point mass since it has no rotation. And so the object has only translation forward, but it has no rotation. So we can just use normal kinematic equations to describe the motion of this object. So if you look on any physics formula sheet, one of the equations or one of the kinematic equations is that the final x position of the object is equal to the initial x position of the object plus the velocity of the object in the initial velocity of the object in the x direction times the time in which the object is sliding only. And this variable t is exclusively for the period in which the object is sliding only. And that's plus 1/2 times the acceleration in the x direction times the time in which the object slides squared. And so in this kinematic equation, we wrote the velocity in the x direction initially. And so the velocity in the x direction, that's just equal to the initial velocity, which is just v naught. And the variable t stands for the time in which the object is sliding only, and that corresponds to this length of time right here. So the variable t stands for that amount of time for sliding only. And so another kinematic equation is that the final velocity of the object is equal to the initial velocity of the object plus the acceleration in the x direction times the period of time in which the object is sliding. So at this point right here, the object encounters the rough surface with friction on it. And so in this case, we would have to take friction into account in order to analyze the case in which the object is sliding and rotating. Previously, there was no friction when the object was sliding only, but now, since there is friction, the object is going to start rotating since the friction is going to cause a torque. And so the frictional force will oppose the circular object, and then it's going to reduce the initial velocity, or it's going to reduce the velocity of the center of mass, and in return, it's going to increase the angular velocity, because previously the angular velocity was 0 when the object was sliding. But now for an object that's sliding and rotating, the object is going to have an increase in angular velocity, and the velocity of the center of mass is going to decrease. So previously we said that the velocity of the center of mass So previously we said that the velocity of the center of mass was a lot greater than the angular velocity, and that was the case in which the object was sliding only, because the angular velocity was 0 and the velocity of the center of mass was equal to v naught. Now the frictional force is going to oppose this velocity of the center of mass. It's going to reduce this velocity for the center of mass, and it's going to point in the opposite direction to the velocity of the center of mass, and by doing that it's going to oppose that, decreasing the velocity, and in return it's going to generate a torque which is going to cause this angular velocity to increase. And that's what's going to happen for the object that slides and rotates. So let's draw where the frictional force will point on this diagram right here. Since the surface is rough and it has a friction on it, the frictional force will point in the opposite direction to the motion of the object, just like this. And so initially the object had the velocity of the center of mass of the object was v naught, but now since the force of kinetic friction points in the opposite direction to this velocity, the new velocity of the center of mass will now be decreased due to this frictional force. So the new velocity for the center of mass will actually be less than the original velocity. So we can write that the new velocity for the center of mass is less than the original velocity. And this is because of the force of kinetic friction points in the opposite direction to the velocity, and that decreases the velocity of the center of mass, and in return, it's going to increase the angular speed. So now the force of kinetic friction will produce a torque about the axis of rotation of the object. And this force of kinetic friction, since it generates a torque, it's going to cause the object to rotate clockwise, just like this. So there's going to be a angular velocity now. And originally there was no angular velocity because the surface was frictionless. But now, due to the force of kinetic friction, or due to the frictional force, there will be a angular velocity due to a torque. So if we relate this scenario to the non-slip condition, the reason why the object is sliding and rotating is because the non-slip condition is not satisfied. So as long as the non-slip condition is not satisfied, then the object is going to continue to slide and rotate. So the force of kinetic friction is going to oppose the velocity of the center of mass, and it's going to try to increase the angular velocity by applying a torque. And it's going to continue to do that until the non-slip condition, or this condition right here, is satisfied. So the force of kinetic friction is going to try and increase the angular velocity by applying a torque about the axis of rotation of the object, and since the force of friction is pointing opposite to the velocity, it's going to cause this velocity of the center of mass to decrease. And that's the reason why the velocity of the center of mass is less than the initial velocity, because the force of kinetic friction is going to oppose it. So what we can say in this case is that since the object is still in the process of sliding and rotating, the non-slip condition is still not satisfied because the object is still sliding and rotating. And by sliding and rotating, I mean that the force of kinetic friction is still trying to decrease the velocity of the center of mass. So the speed of the center of mass is going to decrease because it's opposed by the frictional force, and the frictional force generates a torque. So, and that's in turn going to increase the angular speed. And so that's why the non-slip condition is still not satisfied. The time, or the motion in which the non-slip condition would be satisfied is for the case in which the object is rotating without sliding. In that scenario, the non-slip condition would be satisfied. But since for right now, the object is sliding and rotating, the non-slip condition for right now is not satisfied. And so let's describe the motion of the object when it's sliding and rotating. And so since the object is sliding and rotating, note that there's a frictional force, or a net force, which acts on the object as it slides and rotates. And so we would have to take that into account. But note that previously, that when the object was sliding only, there was no friction on the ball or on the object. So we didn't have to take any frictional forces into account in our motion equations. But now, since there is a force involved, or there is a net force involved, we would have to take that net force into account when we're describing the motion of our object. So if we write Newton's second law, what we have is that the sum of the forces is equal to, so F equals ma, or the mass of the object, times the acceleration of the center of mass of the object, which I denoted with the subscript cm, and that's equal to the force. Now the only force that's the net force that's acting on the object right now is the force of kinetic friction. And since the force of kinetic friction points in the left direction, it would be a negative force. So we would put a negative sign. Let's expand this equation out further. So the formula for the force of kinetic friction is the coefficient of kinetic friction, which is mu subscript k, times the normal force. Now the normal force is just the mass of the object times the acceleration due to gravity. And in front of that is a negative sign. Now let's simplify this down further. Note that both sides have an m, and so if we solve for the acceleration of the center of mass, we get that it's the negative mu, the coefficient of friction times the acceleration due to gravity. Now let's try to make sense out of this. Why is the acceleration of the center of mass negative? So initially the velocity of the center of mass was v naught, and that was for when the object was sliding only. But now, since the object encountered the rough surface with friction, the force of kinetic friction is going to oppose that velocity of the center of mass, and it's going to decrease that velocity of the center of mass. And so the final velocity of the center of mass is going to be less than the initial velocity of the center of mass, because the frictional force is the force that's opposing the velocity of the center of mass. And so that's why the acceleration of the center of mass is negative, because the velocity of the center of mass is decreasing as the object goes from sliding only to sliding and rotating because of the frictional force. The force of kinetic friction is the force that's opposing the velocity of the center of mass. And in return, that force of kinetic friction is going to increase the angular velocity by creating a torque about the axis of rotation of the ball. And it's going to increase the angular velocity, but then it's going to decrease the velocity of the center of mass. So now we have a formula for the acceleration of the center of mass of the ball. So simply all we have to do is we can still use these kinematic equations that we originally had, but instead we would have to plug in our new acceleration into these kinematic equations. And just to note, when the object is sliding only, the acceleration in the x direction is 0 because there is no net force on the object. So whenever the object is sliding only, the acceleration in the x direction is 0. But since in this case the object is sliding and rotating, there is a net force which acts on the object, which means that the acceleration is going to have some value. And that's the value we found right here. And so all we would have to do is just plug in this acceleration of the center of mass into each of these individual equations, because this is the new acceleration of the center of mass. So by simply plugging in this new acceleration, we can describe the motion of this object as it slides and rotates. Now the next variable to define is the variable t, which stands for time. And in our original equation, the variable t stands for the amount of time that the object is sliding only, but for our new variable t, in that's the amount of time that the object is sliding and rotating. So that just on the diagram, it just corresponds to this length of time right here. When the object starts to initially slide and rotate to when the object stops sliding and rotating. So at this point right here on the diagram, right here, this red mark indicates the time, or it indicates the starting point at which the object is sliding and rotating. Then the object is going to stop sliding and rotating at this point right here. And at this point, the object is going to start rotating without sliding. And so the variable t is going to correspond to this amount of time right here. That's what the variable t stands for. Or it just indicates the period of time in which the object is sliding and rotating. And that difference in time is due to the force of kinetic friction acting on the object as it starts out at 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 the start of the rough surface, and as it goes from the rough surface to the point at which it starts to rotate without sliding. And so this difference of time is due to the force of kinetic friction is trying to decrease the speed of the center of mass, and in return it's going to increase the angular velocity. That's what causes this difference of time. The force of kinetic friction is causing this difference in time. Now let's analyze the motion for an object that is rotating without sliding. And so for an object that rotates without sliding, we know that this condition right here, the non-slip condition, has to be satisfied. So since the non-slip condition is satisfied for an object that rotates without sliding, that means that the velocity of the center of mass has successfully decreased enough, and the angular velocity has successfully increased enough, and both of these have, and what caused this was due to the force of kinetic friction. The force of kinetic friction successfully decreased the velocity of the center of mass, and it successfully increased the angular speed. And it did that enough to the point at which the object could start rolling without slipping. So let's analyze that motion. So I labeled time periods on our diagram so we can avoid any confusion. The time period t1 right here corresponds to the time in which the object is sliding only, and the time period t2 corresponds to the period of time in which the object is sliding and rotating. And so let's now analyze what it is like for an object to undergo rolling without slipping. So since the object is now rolling without slipping, it reached a final angular speed of omega subscript f, which stands for final angular speed. And this final angular speed was reached because of the force of kinetic friction, which which generated a torque, which in return increased the angular velocity. So that's how the angular speed, the final angular speed, is now omega subscript f. And the force of kinetic friction has now reduced the velocity of the center of mass to a new velocity, which is v subscript f for final speed of the center of mass. And that new speed is equal to the velocity of the center of mass, which is less than the initial velocity. And it's less than the initial velocity because the force of kinetic friction opposed that velocity, and it decreased it from the initial velocity. Now, whenever an object rolls without slipping, the point of contact between the object and the surface has a velocity of 0, which is shown right here. The red dot is the point of contact between the surface and the object, and that point is instantaneously at rest, so we can just say that the velocity at that point is equal to 0. But the velocity of other points on the object, like the velocity of the center of mass, those still have actual values and are not 0. Like the velocity of the center of mass is still going to be less than the initial velocity v naught. And so notice that the object is rolling counterclockwise. Or no, sorry. It's rolling clockwise in this direction, because that's the direction that the angular velocity points, clockwise. And so that means that there has to be a force that's causing the object to rotate clockwise, and that force would have to be the force of static friction. And previously, the force acting between the contact point was kinetic friction, but in this scenario, the force acting between the contact point of the object and the surface is static friction, and I'll denote that with the F subscript S for F static. And the reason why it's static friction is because, remember, I said earlier that the point of contact between the object and the surface is instantaneously at rest. So the velocity of the dot shown at the bottom is 0 instantaneously. And so since that part is at rest, the force is going to be static friction, not kinetic friction. So now let's analyze the motion of the object. And also, since the object is rolling without slipping, we know that the non-slip condition is satisfied in this case, because the velocity of the center of mass has decreased enough from its initial velocity, and the angular velocity has increased enough until this condition is satisfied. So now let's come up with equations of motion to describe the object. Let's say that the object begins to roll at an angle of theta subscript I for theta initial. And let's say it rolls through an angle until it reaches angle theta subscript F for theta final. Now the angular displacement is just going to be the difference between these two values. that means that the object rolled through an angle of of theta final minus theta initial. That would be the angular displacement. So now we can write equations of motion which are similar to these earlier equations of motion in kinematics, but now we can apply those kinematic equations to rotational kinematic equations. And these equations will be very similar these to these kinematic equations for sliding only. So one of the kinematic equations, or one of the rotational kinematic equations, is that the final angle of the object is equal to the initial angle that it starts at plus the initial angular speed times the time period in which it rolls without slipping, plus 1/2 the angular acceleration times t squared. And so all I did was I just wrote an equivalent expression of the normal kinematic equations, but I just wrote it down for rotational kinematic equations. Now let's write a rotational kinematic equivalent of the second equation right here. We know that the final angular velocity is equal to the initial angular velocity plus the angular acceleration times the time period in which the object rolls without slipping. And if we write an equivalent expression to the last kinematic equation right here, we could write a rotational equivalent of that, and we get that the final angular velocity is equal to the initial angular velocity plus 2 times the angular acceleration times the angular displacement, or the change in the angle. So note that in these rotational kinematic formulas, we use a angular acceleration. And so what we need to determine now is the angular acceleration, is it negative or is it positive? Now, a negative angular acceleration would indicate that the angular speed is decreasing over time. And a positive angular acceleration would indicate that the angular speed is increasing over time. And this is because that the rate of change of the angular speed over time is equal to the angular acceleration. So if the angular acceleration is decreasing over time, that means that there's going to be a negative angular acceleration. And this is similar to normal kinematics, because in normal kinematics over here, for an object that was sliding only, let's say that the object had, when it was sliding only, let's say it had a positive angle, a positive acceleration, a positive linear acceleration. That would indicate that the velocity of the object is increasing. And a negative acceleration would indicate that the velocity of the object is decreasing over time. So we can just compare. So notice how normal linear acceleration is very similar to rotational angular acceleration. So now which of these two values is it? is the angular acceleration positive or is the angular acceleration negative? So in order to determine if the angular acceleration is negative or positive, we have to look that as the ball starts from its initial sliding only scenario and as it encounters the rough surface, is the angular speed increasing or is the angular speed decreasing? So notice that when the object was sliding only, that the object had an angular speed of 0. And then when the object encountered the rough surface right here, the force of kinetic friction caused a torque, which in turn increased the angular speed. So the angular speed went from 0 to some value greater than 0. And the velocity of the center of mass also decreased due to the force of kinetic friction. And the angular speed increased due to the force of kinetic friction creating a torque. So as the object went from sliding only to sliding and rotating, the angular speed actually increased because it went from an angular speed of 0 to an angular speed of something greater than 0. So, and in our diagram, one way to look at it is that initially the object had only translation and there was no rotation, but now in the final position in which the object is rotating without sliding, the object is going to rotate and it's going to translate as well. So it's going to and during that process the angular speed actually increased as it went from a value of 0 to something greater than 0. And since the angular speed increased, we know that the angular acceleration has to be positive because the angular speed was increasing throughout this entire process. And so the angular acceleration has to have a sign of positive. And so initially we can say that the angular speed was 0, as I drew on the diagram. But now the angular speed is something greater than 0. It's some non-zero value. And the force of kinetic friction created a torque to increase that value of the angular speed from 0 to something greater than 0. So these are the three different scenarios in which an object is sliding only, and then when it encounters a rough surface, it's going to slide and rotate, and then after some period of time, once the non-slip condition is satisfied, it's going to roll without slipping. So these are the three different types of motion that an object can have when the surface has no friction and when the surface does have friction.